Radioactive sample. How we find the mean life? Let us try to compare this with what we did in alternating current. We had in x-axis current, in x-axis time, in y-axis current. Suppose if the curve is like this. To find the average value of I, you have to find the total area. In the total area, you get the product of y-axis and x-axis, which is I and t. When you divide by t, you will get the average value of I. For that, what we did, we took the instantaneous value of current is I. At that time, this is dt. So the area of the strip is I dt. If you integrate for one full cycle, when you integrate from 0 to 1 full cycle, you get the average value of I and t. When you divide by time, which is for the same full cycle, you get the average value of I. In the same fashion, suppose you have in the y-axis number of atoms, in the x-axis time. So this graph would be like this. Here you are not interested in finding the average value of n. You are interested in finding the average value of the time. Let's assume that at time t dash, some small number of atoms are decaying. Let that atoms dn. So this dn atoms has a lifetime of t dash. Suppose after t double dash, another small number of atoms are decaying. So this dn number of atoms has a lifetime of t double dash. So you are supposed to add t dash into dn plus t double dash into dn. When you add all of this, it will be like integral t dn. Since you are interested in only the time, the average of these time, you are supposed to divide by total number of atoms. Hence the mean life, the average life is represented by the letter tau, which is given as integral t dn integrated from. At this point, at t equal to 0, the number of atoms will be equal to n0, which is the initial number of atoms. So this graph does not touch the x-axis because the last of the atom that decays only after a very long time, which is considered to be infinity. For example, if you start with 1 lakh atom and the lifetime of radioactive half-life of the radioactive sample is 100 years. After 1000 years, 1 lakh atom becomes 50,000. After 1000 years, 50,000 becomes 25,000. Like that, if you go on, for the last 2 atom to become 1, again 1000 more years will happen. So the last of the atom decays after almost infinite time. So at t equal to infinity, the last atom decays, hence you'll be left with 0 atoms. Hence the integration for the time should be carried from 0 to infinity by integral dn. So at time t equal to 0, we have initial number of atoms n0. After infinite time, you have left with 0 atom. So it is integral dn to be integrated from n0 to 0, which means tau is equal to t dn. So from Rutherford-Sardi law, you know that n is equal to, we write that here, n is equal to n0 e power minus lambda t. Then dn by dt equal to n0. When you differentiate e power minus lambda t, it is e power minus lambda t into d by dt of minus lambda t becomes minus lambda. Hence dn is equal to minus n0 lambda e power minus lambda t into dt. So I'm just writing that integral t into dn is minus n0 lambda e power minus lambda t into dt. Integration from 0 to infinity whole divided by integral dn is n, that is to be integrated from n0 to 0. So let us take the constants out. Minus n0 lambda to be taken out. Integral 0 to infinity t e power minus lambda t dt whole divided by upper limit 0, lower limit n naught. So 0 minus n naught. So minus n naught and this minus n naught will be cancelled. Hence our tau value is equal to lambda into integral 0 to infinity t e power minus lambda t dt. So this has to be done using integration by parts. You consider this as u, this whole part as dv. If this is u and this is dv, u equal to t, hence du is equal to dt, and dv is equal to e power minus lambda t dt. Hence when you integrate, integral dv becomes v. E power minus x, when you integrate, it is e power minus x only divided by minus lambda into dt, right? Integral dt is this thing. So substituting that, how do we integrate u dv? So the integration u dv is given as uv, for that also limits to be applied, minus integral v du. So the limits has to be applied, 0 to infinity, 0 to infinity. But we have one lambda out, hence tau is equal to lambda times uv. U is t, v is e power this thing. So t e power minus lambda t by minus lambda 0 to infinity minus integral v e power minus lambda t by minus lambda into du is dt, 0 to infinity. So then the next steps are, lambda is out, and here when you substitute upper limit, so t is infinity, e power minus infinity into lambda becomes minus infinity, by lambda will be minus, lower limit t is 0, so t is 0, e power minus 0 into lambda is 0 divided by minus lambda. Take this minus lambda, and after that minus into minus becomes plus. I am taking 1 by lambda out, integral e power minus lambda t dt 0 to infinity. So what happens here is e power minus infinity comes to the denominator, e power plus infinity, e power infinity is infinity, 1 by infinity is 0, 0 into anything becomes 0. In that way this whole term becomes 0. Here 0 into anything becomes 0, this term will also become 0. Hence the mean life of a radioactive sample, lambda into 1 by lambda into integral e power minus lambda t dt, e power minus lambda t by minus lambda, we have to integrate 0 to infinity. So this lambda and lambda will be cancelled, so we can take tau is equal to minus 1 by lambda out, e power minus lambda t 0 to infinity minus 1 by lambda, and when I substitute upper limit, e power minus infinity, e power minus infinity, when I substitute lower limit, e power 0. So e power infinity is 1 by minus infinity is 1 by e power infinity is 0. So infinity, 1 by infinity becomes 0. So 0 minus 1. So that is minus 1 by lambda into 0 minus 1. So 0 minus 1 is minus 1. Minus 1 into minus is plus. Hence the mean life of a radioactive sample is the reciprocal of the decay constant. We know lambda is decay constant. Hence mean life of a radioactive sample is 1 by decay constant.